Hello, welcome back. In this video, we are going to learn about data link control. So what is the agenda? We will be learning about the various design issues of data link control, then framing, after that flow and error control. Then we will be learning about the protocols of noiseless channels, after that few protocols of noisy channels, and then HDLC or high level data link control. Let us look at the design issues. Data link layer has many functionalities. The first functionality is the data link control and the second one is the media access control. Now what is the meaning of data link control? Data link control means designing to communicate between two nodes. Basically this is done for node to node communication. And media access control means how the nodes share the link. For sharing, there are three different techniques. We will learn them one by one in the later videos. One is the random access. The second one is the controlled access. And the third one is the channelization. In this video, we are going to learn about the design issues of data link control. So the main functionalities of data link control are framing, error and flow control. So here we will be learning about the framing for bit-oriented protocol and framing for byte-oriented protocol. And regarding the error and flow control, we will be learning about few protocols of noiseless channels and some protocols of noisy channels along with HDLC. Let us understand what framing is all about. The physical layer transmits the raw bit streams by converting them into signals. These are electromagnetic signals which can pass through the channel. Now when from the physical layer, the bit streams pass on to the data link layer, the data link layer forms the frames. What is the meaning of forming the frames? The meaning is segregating the bits into different frames. These frames can act as delimiter. So for a particular bit stream, we can have several frames. These frames will have a header and a trailer along with the payload or the data. This header basically gives the source and the destination address, and the trailer is used for error detection and other coordination and control information. We can think of this frame as the post office letters. Now in the letter box, we can have several letters or envelopes. Now in each envelope, there can be some letters. Now this letter box consists of several envelopes having several letters. Now these letters can be the bits and these envelopes can be the frames. So envelope act as delimiter. Now why do we divide them into frames? We can very well keep all the bit streams together and transmit them to the upper layer or the network layer. But in doing so, if there is any error, then error detection and correction technique must be performed on the entire bits, which is very cumbersome and time consuming. So that if they are segregated into smaller size manageable frames, then it will be easier for error detection and correction techniques. Now framing can be of two types. One is fixed size framing and the other one is variable size framing. In fixed size framing, the framing bits are fixed and this is basically used in ATM or asynchronous transfer mode. For variable size framing, we can have framing bits which are variable in nature. And this can be either for character-oriented approach or bit-oriented approach. For character-oriented approach, we can use the text type of data, and for bit-oriented approach, we can use either text or graphic or audio or video data. Let us understand the character-oriented approach of framing. Let us understand the bit structure in framing. So here there is a term which is called byte stuffing, which we will learn very shortly. Let's say this is the data from the upper layer that is coming to the data link layer, and when it comes to the data link layer, we have to add one header that consists of the source address or the destination address and the trailer, which consists of the control information along with the error detection and correction codes. Now this flag is added at the beginning and at the end. These are all 1 byte. Since this is character oriented, we have 8 bits or 1 byte. So 1 byte flag is added at the beginning and at the end. This acts as a delimiter so that the receiver understands that this is the start of the frame, and when it reaches the other flag, it understands that this is the end of the frame. But what happens if the data itself from the upper layer consists of some flag-like byte? Then the concept of byte stuffing is introduced. Because if the receiver is in the middle of the frame, accessing the frame, and it sees that there is a flag byte, then it understands that this is the end of the frame. Even though it may not be the end of the frame, and this flag can be a part of the data. Normally this flag is kept as a byte which is not used for normal text type of data. But when we are using it for audio, graphic or video type of data, then this flag can be a part of the data and problem arises. So what happens, what we do whenever there is a flag type of data in the upper layer, we put one extra byte which is the escape character. This escape character will be placed whenever there is a flag type of data, or even this escape type of character can be there in the data. So again you have to place one escape type of character here before this escape. So escape character will be placed before the flag or even the escape. So these two extra bytes are then stuffed in the original frame. And when you are receiving the frame, you will receive these extra bytes. And at the receiving end, we know that these are the extra bytes and they should be removed, and unstuffed data will be received. So this is the framing structure of character-oriented protocol. Now there is a serious disadvantage of this type of character-oriented protocol because it uses 16 or 32-bit as opposed to the 8-bit which is used over here. Let us understand now the bit-oriented protocol. And here, just like the character-oriented protocol, we will have the concept of bit stuffing. Now the flag for bit stuffing is a 8-bit number that starts with 0 and then there are 6 ones and ends with 0. So 8 bits. So let us understand them with the help of this example. Let's say we have the data from the upper layer and it consists of these numbers. Since the frame that should be sent should have a flag at the beginning, and then there should be the header part. At the end there should be a trailer part, and then again it should end with a flag. Now this, as before, we know this flag is given to form the delimiter so that the receiver knows that this is the start and the end of the flag. And the header part gives the source and the destination address, and the trailer part is used for control information. Now since the flag is of this nature, whenever in the data there is a 0 followed by 5 ones, a 0 followed by 5 ones, a 0 should be inserted in between so that even if 1 comes after it, then it should not be mistaken for a flag. So this is known as bit stuffing as opposed to byte stuffing in the byte-oriented protocol. So here there are consecutive 5 ones. So here 1 0 is stuffed. Again here also there are consecutive, so again 1 0 will be stuffed over here. So you see here the 0 is stuffed. So at the receiver, then this 0 can then be removed and it can be unstuffed. Let us understand flow and error control. What is flow control? When the sender is sending some data and the receiver is receiving some data, the sender is sending at a data rate and the receiver is also receiving at a particular data rate. If the data rate of sending is more than the data rate of the receiver, by which the receiver can process the data, then the receiver will be overwhelmed with data and there will be queuing of data. So proper measures should be taken for flow control mechanism. It is basically a set of procedures that restricts the quantum of data a device can send before waiting for acknowledgement. So what we do, we give a mechanism of acknowledgement, like some amount of data will be sent from the source to the destination or the receiver, and the receiver will acknowledge. Only when the sender receives the acknowledgement, then it can send the next set of data. So this way, flow control mechanism can be accomplished. Another one is the error control mechanism, which is done by automatic repeat request or ARQ. And basically this is done by retransmission of data. How do we understand whether the data that is received is error-free or not? So error control is basically a part of error detection and correction techniques where we use redundancy. Redundancy means adding extra bits to understand whether the data is erroneous or not. Another way is retransmission of data. And these two retransmitted data are compared, bit by bit compared, and if there is any discrepancy, then the data is rejected at the receiver, otherwise it is accepted. Now let us go and look at the various noiseless channels. Here we consider that the channel is noiseless. That means there is no interference to change or modify data. So this is a perfect condition, but in reality this is not possible. So we are thinking of an idealized situation. So there are two protocols. Number one is the simplest protocol, and this has no flow control and error control. We think that the rate at which the transmitter is transmitting is the same as the rate at which the receiver is processing the data. So there is no need of flow control, and since there is no noise, there will not be any error in the transmitted data. The second one is a bit sophisticated one as compared to the simplest protocol, and this is called stop-and-wait protocol. This has the flow control mechanism, but without any error control. So let us look at the simplest protocol design. Here this is the flow diagram of the simplest protocol design. We have the sender side. The network layer gives the data to the data link layer. So data link layer is getting the data from the network layer. It passes on to the physical layer as frames, and from the physical layer, the raw bit streams are passed on to the receiver side. At the receiver side, again, the physical layer receives the data frames, and it passes it on to the data link layer, and then it delivers the data to the network layer. Now, what are the events that are happening at the sender side? The events that are happening are requests from the network layer. Unless there is a data coming from the network layer, the data link layer cannot process the data. So, the algorithm at the sender side is repeating forever. Whenever the data comes from the network layer, it processes it. What happens at the receiver side? There again is the event. It has to have a notification from the physical layer that it has received a frame. And at the receiver side also, the algorithm repeats forever. Let us understand stop and wait protocol design. Here, flow control mechanism is added to the previous one. So there are number of events that are happening at the sender side. Other than the previous one, an extra event that will be happening is the notification from the physical layer of the receiver. Whenever the data frame is coming from the sender side physical layer to the receiver side physical layer, whenever the receiver has received the data, it will send an acknowledgement frame back to the sender. So this is the event that is happening at the sender side. And what happens at the receiver side? It has to have the same notification from the P layer that it has received a frame, and nothing more than this. So this is the stop and wait protocol design for noiseless channel. This is same as the simplest protocol with the added functionality of flow control. Next we look into the noisy channels. For noisy channels, we think that there is noise, and so there can be interference, and zeros may be changed to ones and vice versa. So flow control and error control mechanisms must be integrated. So the very first protocol is stop and wait automatic repeat request. It has the same functionality as the stop and wait protocol with the added functionality of error control. The second one is go back and automatic repeat request. This has a more sophisticated approach as compared to stop and wait automatic repeat request. And the last one that we will be discussing here is the selective repeat automatic repeat request. So stop and wait automatic repeat request design. So this is the flow diagram of the stop and wait ARQ. As before, we have the sender side and the receiver side. The data are sent from the sender side, goes to the receiver side, and an acknowledgement frame is received. But here, there is an added functionality of error control. the receiver will check for error of the data frame, either by retransmission or by redundancy techniques. So if it finds that the data is erroneous, it will remain silent without sending the acknowledgement frame, meaning that it has discarded the data. Otherwise, if it receives the proper data or the data which has integrity, it will send back the acknowledgement frame to the sender. Here at the sender side, so the sender should have a sequence number. Sender should have a sequence number for the frame to send, and so the sender will have this sequence number will be basically the next frame to send, and at the receiver side again we have a number where it indicates that the next frame it should receive. And if there is a timeout that should occur, it should again resend the frame from the sender end. Because during this timeout, if it does not receive the acknowledgement frame from the receiver, it should resend the frame. So this is the stop and wait automatic repeat request design. This is go back in automatic repeat request design. In the previous one, we have seen that acknowledgement is sent for every packet. Now this is more sophisticated design in the sense that the transmitter can send a large number of packets at a time without receiving the acknowledgement for each packet. For example, it can send 1, 2, 3, 4. So these are the sequence number of packets that are sent from the sender into the receiver end, and the receiver can then send the acknowledgement with the help of an acknowledgement number corresponding to the sequence number of the frames that it has received properly the frames. Now, suppose it has sent 4 frames and the receiver has given acknowledgement for the first, and it has not received, the sender has not received acknowledgement from the receiver of the second frame. It can even receive acknowledgement of the 4th frame. So in that case, there should be a sliding window which will indicate that since it has not received acknowledgement of the second frame, this window will indicate that it has to go back to the second frame and resend all the frames. That is, it should send 2, 3 and 4 once again. So this is known as go back in automatic repeat request. Next, let us understand a much more sophisticated noisy channel protocol. This is selective repeat automatic request. Automatic repeat request. It is the same as go back in, with the only exception that if it has sent 1, 2, 3, 4 and has received acknowledgement for 1 and 4 and 3 but has not received acknowledgement for 2, in the previous case it had to go back to 2 and resend all these frames. But here it can selectively send the second frame for which it has not received any acknowledgement. So this is selective repeat automatic repeat request. Let us understand high level data link control. So this is high level data link control protocol. It is basically a bit oriented protocol as compared to the byte oriented protocol which we have been learning so far. There are various configuration modes of HDLC. One is the normal response mode and the other one is the asynchronous balance mode. Now this normal response mode is unbalanced in nature, because there can be one primary and large number of secondaries to which it can be connected. So this is unbalanced. So in normal response mode, there can be 2 types of configurations. One is for point to point and the other one is for multi-point. For point to point, there is only one primary and one secondary. The primary gives the command and the secondary gives the response. For multi-point, there can be one primary and several secondaries. So primaries always give command and the secondaries give responses. For asynchronous balance mode, the stations are combined in the sense they can give command as well as response. So here we have one station and here we have another station. Both are in the combined mode. Both of them can give command as well as response. What are the frames of HDLC? The frames are information frames or iframes which are used to transport user data and control information. Then we have the supervisory frames or S frames. They are used to transport control information. And the unnumbered frames or U frames reserved for system management. This is the frame structure of HDLC. For the I frames, we have the flag, then address, then control, then user information, then frame check sequence, and followed by again another flag. For supervisory frames, we have flag, address, control, frame check sequence, and the flag. Here you see the user information is missing. For unnumbered frames, we have flag, address, control, management information, FCS, and the flag. Let us look into detail of the control field of various frames. We have information frames, supervisory frames, and unnumbered frames. So these are the control fields. Starting with 0, then NS, PF, NR. And in the supervisory frames, we have 1 starts with 1, then 0, then various codes are there, and then PF, NR. And also the unnumbered frame starts with 1 and 0, then there are different codes, PF and then codes. So for the supervisory frames, based on the code structure, we can have RR frame, RNR frame, reject frame, and S reject frame. So if the code is 00, we will have RR frames. If the code is 10, we have receive not ready. So this is the receive ready, this is receive not ready. If it is 01, then it is reject, and if it is 11, it is selective reject. These are the U frame control command responses. So these are the different codes. Correspondingly, we have the command and response and their meaning. So this is the snapshot of the different codes, command, response, meaning. To summarize, in this video, we have learned about the various design issues of data link control. We have understood the framing structure. We have touched upon noiseless and noisy channel protocols. And we have looked into HDLC or high level data link control. Thank you.